This is part 3 of thermal physics, and we're going to derive the pressure of an ideal gas. Consider a gas particle inside the cubic box shown. The particle has a mass of m and it's travelling at a velocity of u. Let's say it hits the wall marked A of the box. Let's think about momentum first. Momentum is mass times velocity, so it's mu. How does the momentum change due to the collision with the wall marked A? Well, the velocity is travelling in one direction, which is positive for u, and when it's travelling in the opposite direction after the collision, the velocity is going to be minus u. So the change in momentum is mu minus mu, which gives us 2mu. That's the change in momentum. Second step is that you have to think about the equation for velocity. So velocity is distance over time, and if we rearrange that equation, then time must equal distance divided by velocity. So let's think about the time between collisions. Well, we've got the time equals distance divided by velocity. What's the distance the particle travels between collisions? Well, it travels from wall A, a length of L, to the opposite wall, and then back again to wall A. So it travels a distance of 2L between collisions. So the time taken is 2L divided by the velocity, which is u. Now force is the rate of change of momentum, which is the change in momentum divided by the time. So we worked out the change of momentum in part 1, and now we have an equation for the time. So we put that into the formula, and we come out that the rate of change of momentum is equal to mu squared divided by L. So that's the force as well. And pressure is force divided by area, and the area of that wall is L squared because the cube has sides of length L. If we put that into the equation for pressure, we have that pressure is mu squared divided by L cubed, and of course L cubed is an expression of the volume of that box, or the volume of the gas. So here we are, pressure is mu squared divided by volume, but we've just worked out the pressure exerted by one particle of gas. We've got more than that in the box. We have, say, n particles of gas in the box. Now, we can say that a third of these particles will be hitting the walls from side to side. Another third will be hitting the walls in an up and down direction, so they'll be hitting the top and the bottom walls, and the final third will be hitting the front and back walls. So you'll have a third of the particles each moving in the different three-dimensional planes. So the pressure for the total pressure of the gas will be the number of particles divided by 3 multiplied by the mass multiplied by c squared, I'll come on to that in a minute, divided by the volume. So what's c squared, because we had u squared in the original formula for pressure? Well, each particle of gas will be travelling at a different velocity. So what we need to do is to find the average square velocity. So we take each individual velocity, square it, add it together and divide it by the number of particles to find c squared. And that is how we derive the pressure of an ideal gas. Pressure of an ideal gas, P, is n mc squared divided by 3v. Let's move on now to the properties of an ideal gas. Well, this pressure is true if it is an ideal gas, and these are the conditions necessary for an ideal gas. Condition 1. The gas must contain a large number of particles. 2. The particles must move rapidly and randomly. 3. The motion of the particles must obey Newton's laws. 4. The collisions between the particles or between the particles and the wall must be perfectly elastic. There must be no attractive forces between the particles. The forces that act during the collisions must be instantaneous. And finally, the particles must have negligible volume compared to the size of the container. And those are the properties of an ideal gas. And that concludes part 3 of thermal physics.
Created using Powtoon.